Okay, so we've started framing this idea how there could be feedbacks in terms of the consequences of global warming. And broadly speaking, I like what your book does where it tries to sort these feedbacks out into two piles, the so-called fast feedbacks and the slow feedbacks here. The fast feedbacks are feedbacks that happen, changes that happen almost immediately when you make a change to the climate system. They are something that happens directly as a consequence of the changing surface temperature, more or less right away. And one of them we've seen already, the ice albedo feedback. If we warm up the ground and the surface of the Earth and ice melts and exposes more ground, that immediately starts absorbing radiation, the temperature starts going up, you get even more melting and so on. That is a positive feedback between ice albedo and temperature. That happens almost immediately. It's a fast feedback. So the water vapor feedback is another one. The water vapor feedback is another positive, fast feedback. And it depends on the fact that the amount of water vapor the air can hold depends on the temperature of the air. Warm air holds more water vapor than cold air does. And remember, water vapor is a greenhouse gas. And so if I wanted to draw one of these diagrams that illustrates what's going on in the water vapor feedback, if we start with some initial warming due to greenhouse gases in the atmosphere, well, the air can now hold more water vapor. We have a higher humidity in the air. Alright, but water vapor is a greenhouse gas, and so we're going to have a stronger greenhouse effect going on in the atmosphere, which means the surface of the Earth will get even warmer. But then if it's warmer, don't we get even more water vapor? Sure we do. And does that mean there's even higher humidity and more greenhouse gases and the planet gets even warmer and warmer? Sure. The water vapor feedback is a fast, positive feedback. It amplifies the original change. And we say fast because, I mean, as soon as the air warms up, the air will hold more water vapor. It doesn't take a decade to evaporate water. It happens more or less immediately. Another fast feedback is the awkwardly named lapse rate feedback. I'm not going to worry about parsing that name for you, but just remember the name is lapse rate feedback. And the lapse rate feedback is a negative fast feedback. And it's based on this idea that, well, it's kind of loosely based on Stefan Boltzmann's law. It basically says that the warmer the ground gets, the more radiation the ground emits. And so we sort of have this negative feedback. I kind of changed the way I structured this diagram here. If we started with the initial warming that made the ground warmer, well, by the Stefan Boltzmann law, that means the ground's going to emit more long-wave radiation. And if the ground emits more long-wave radiation, it cools back down. Okay, this is a type of feedback, right? I mean, the amount of radiation the ground gives off does depend on the temperature, and emitting more radiation cools the ground back down. Okay, that's the lapse rate feedback. And again, it's a very fast feedback. It isn't like the ground will wait a decade and then emit the radiation. As soon as the ground is warmer, it's emitting more radiation. The fourth one I listed here is a whole complicated issue. It's called the cloud feedback. And the cloud feedback and the role of clouds in climate change is actually one of the most complicated of the ongoing problems in climate science. I'm going to switch to a slightly different version of an energy balance type diagram here to show you what I'm talking about. Clouds in the atmosphere play two important roles with regard to the energy balance. We'll call role 1 what they do with regard to shortwave radiation. By and large, clouds reflect shortwave radiation from the sun and keep it from reaching the surface of the Earth. That is a role that is keeping the Earth cool. On the other hand, we'll call it role 2, is a long-wave role for clouds. Clouds act like a greenhouse gas. They're not a gas, but they act like a greenhouse gas. They absorb long-wave radiation that the surface of the Earth emits, and then they themselves emit long-wave radiation back down to the surface of the Earth. That is an impact that keeps the surface of the Earth warm. So there are two main roles to how clouds act in the atmosphere. Now at the present time, role 1 is bigger than role 2 in our climate. It took science a long time to figure that out, but currently our cloud feedback works something like this, where initial warming due to greenhouse gases makes for higher humidity and also makes for more rising motion. Clouds are due to rising motion in the atmosphere. You get more clouds, but the clouds keep shortwave radiation from reaching the surface of the Earth. They keep the Earth cooler, you get less warming, and they kind of... So the original warming is then contradicted by the clouds and then the reduced warming that happens afterward. It's a fast negative feedback. But it doesn't have to always be that way. In fact, there's some suggestions that in the future, role 2 will be bigger than role 1. It kind of depends on how much warming will happen. But if that happens, we get a positive but fast feedback where more warming due to greenhouse gases will mean higher humidity and more clouds, but those clouds will mean even more of a greenhouse effect, which means even more warming, which means even higher humidities and more clouds, and we'll have a positive, fast feedback. Again, it doesn't take a decade for those clouds to form. They form more or less immediately. It's a fast feedback. We better hope that doesn't happen, by the way. Earth would turn into something similar to Venus if we had a fast, positive feedback in the cloud effect, in the cloud feedback. Let's switch to the slow feedbacks here. The slow feedbacks happen slowly because the changes that happen take decades or even centuries to happen in response to changes in the surface temperature. First of our slow feedbacks will be the ice albedo feedback. Wait a minute, Dr. Shruggy, wasn't ice albedo feedback already on our fast feedbacks list? Yeah, it was. Kind of depends on what kind of ice you think you're melting here. I mean, if you're just talking like snowpack and it's only a little, a few inches thick and it's got bare patches already and so on, like this little patch of flowers poking through the snow here, that's a very fast feedback. Warm the ground up a tiny bit and all that snow will be gone. Okay, it'll be gone by this afternoon. Alright, on the other hand, it could be a very slow feedback if you're talking about something like an ice sheet, where, this giant slab of ice happens to be East Greenland in that particular picture. If the temperature warms up a degree, yeah, that ice is going to melt. But it could take a century. Okay, that is going to take a long time before that piece of ice melts and you can see the bare ground and the bare ocean or whatever. It's a very slow feedback. The ice albedo feedback depends on how thick the ice is and how quickly it's going to melt as to whether it is a fast feedback or a slow feedback. There's another whole set of slow feedbacks that are called carbon cycle feedbacks. A carbon cycle feedback is a feedback in which initial warming, due to like greenhouse gases and so on, ends up releasing large amounts of carbon dioxide and methane that are currently sequestered in the natural environment. The word sequestered is kind of a hard one to understand. It means like hidden or stored in the natural environment. Let's think about some examples of places where carbon dioxide and methane are stored or sequestered in the current environment. One important place is in the permafrost. Permafrost is soil in the Arctic that is frozen year-round to great depths. Oh, the top inch or two of this, or maybe a little bit more than that in this picture here, might thaw in the spring and plants can grow into it and then it freezes again in the winter. But to great depths below the ground there, the ground is frozen. And when plants that are living on top of permafrost die, they don't generally fully decompose. Rather, because bacteria don't really thrive in that kind of environment where it's frozen and so on, the roots and a lot of the plant material are just permanently locked in ice, certainly for centuries or longer. And that's a lot of carbon that's stored. I mean, a lot of the surface area of the Earth in high latitudes is in the form of permafrost, and that permafrost has all kinds of dead roots and sticks and leaves and stuff in it that are hiding the carbon from the environment. They are sequestering that carbon. Alright? Another place where we store a lot of carbon is in the form of those methane clathrate ices that we talked about way back in the methane lecture, where under high pressure at the bottom, at high pressure but low temperatures, on the continental shelves out in the ocean, there are these ices that form that are made not of water but of methane. And in fact, they could be the largest single source of fossil fuels on Earth. There's an enormous amount of methane stored in them. And the problem is, they're very sensitive to temperature. Even warm the water around them, by a ½ degree Celsius or something like that, and the methane ice returns to methane gas and bubbles out of the ocean and back up into the atmosphere. That would be a very serious situation if suddenly an enormous amount of methane were to bubble out of the ocean over a relatively short period of time. They're both examples of carbon cycle feedbacks where initial warming causes carbon to be released, whether that is by melting permafrost and allowing the leaves and sticks and roots and stuff that are in it to decompose now and return that carbon to the atmosphere, or whether that's by, say, warming the ocean a little bit that makes the methane clathrate ices in the bottom of the ocean return to a gas form and bubble out of the ocean. But either way, you end up with more carbon in the air, and you get an overall stronger greenhouse effect, and then you get even more warming, which melts more permafrost, or makes the ocean warmer, and more methane ices are returned to gases, and so on. But these are fairly slow, albeit positive, but slow feedbacks. By the way, they are slow feedbacks and they are positive feedbacks. They are slow in the sense that it's going to take a long time for these things to happen. Even if you have the temperature warming, it takes a long time to warm the ocean. And so you only have to warm it maybe a ½ degree to start getting these methane ices to return to gas, but it's going to take a long time to warm the ocean that much. It's the same way it takes a long time to melt permafrost. And so, on the order of decades before all that carbon would start returning to the atmosphere. Another important set of feedbacks is one that we saw earlier in the lecture, which was about the vegetation feedback. That is a very slow feedback, again, where an increase in the amount of carbon dioxide causes your trees and so on to grow more. More carbon dioxide is drawn out of the atmosphere and stored in the trees and so on. You lower the amount of carbon dioxide in the atmosphere, and that returns. Now the plants don't thrive as much. Now you get carbon dioxide increasing in the atmosphere, and it's just a negative feedback. It kind of damps the increase in the carbon dioxide. This is a very slow feedback. It takes a long time for the trees to grow enough to have extracted a gigaton of carbon from the Earth's atmosphere. This is on the order of decades that the vegetation feedback works. The final one is probably our slowest feedback that we're going to talk about in this lecture, and that's the weathering thermostat. The weathering thermostat only really works on geologic timescales. It takes like millions of years for this to work. But if you do have more carbon dioxide in the atmosphere, you might remember that one of the ways you can get carbon dioxide out of the atmosphere is by precipitation. A certain amount of carbon dioxide does dissolve into raindrops and form little weak carbonic acid droplets, which then when they fall on the ground can react with minerals and things like that and eventually result in things like limestone and so on. Which eventually, like plate tectonics, can, subduct under ocean trenches and things like that. Well, that's, the Earth isn't old enough to have done some of those things. I mean, this is a feedback, but it's a very, very long feedback to get the carbon out of the atmosphere or those things. We are not going to be around long enough to make that happen. All right, before we have kind of a little closing set of thoughts about this lecture, let's do a couple quick more questions here. Question 4. The water vapor feedback is an example of a blank feedback in the atmosphere. Positive and fast, negative and fast, positive and slow, or negative and slow. What kind of feedback is the water vapor feedback? Pick one of those choices, get a little feedback before you move on to question 5.